It is my distinct pleasure to introduce our next speaker, Professor Saeed Amal. Professor Amal is an esteemed assistant research professor at Northeastern University and a valued member of the Rights Institute research team. Professor Amal's work is a cutting edge of medical science, focusing on the application of artificial intelligence and multimodal data to improve outcomes in the cardiovascular disease and cancer. His innovative approach and dedication to his field have led to significant advancements in these areas. Before joining Northeastern University, Professor Amal honed his research skills as a postdoctoral fellow at the prestigious Stanford University School of Medicine. He also brings a wealth of industry experience to the table, having served as a vice president of an R&D data medical startup specializing in cardiology. Professor Amal's leadership and expertise extend beyond academia. He had made significant contributions to AI-based research in the tech industry, with roles at industry giants such as General Electric and General Motors. Please join me in welcoming Professor Syed Amal. Professor, please go on.
Yeah, thank you for the introduction. Let me share my screen. Okay, so I'm going to talk about artificial intelligence web-based application that we developed for cancer diagnosis and on usability study that we performed for gauging the usability of the tool by giving doctors like pathologists the tool to try and work with that during their diagnosis process, and then to estimate the workload, the efforts, and that are needed for the pathologist to use and to interpret the outcomes the AI outcomes that we are presenting. So I'll just go for overview first on background about prostate cancer. So it's the it's the second most common cancer in men globally, and it's the second leading cause of mortality from cancer. When we talk about the challenges of prostate cancer, of the diagnosis of prostate cancer from biopsies, so we find that increase in volume of the prostate biopsies, shortage of pathologists, and the variability of grading that can result in over-treatment or under-treatment. So there is even the same pathologist can look at the same biopsy after 2 months and can grade it different in some confusing cases. So and it's estimated that 1 out of 6 American men will be affected by this ailment. In terms of number of diagnoses, we have 1 million diagnoses a year and 350,000 death cases a year. So our approach, the first approach, was to develop a machine learning and deep learning models that can mimic the process of the pathologist in terms of diagnosing the biopsy, the scanned biopsy. So the existing workflow today is that the pathologist would take the biopsy, it's essentially stained biopsy, in the slide, would put it on the microscope and would start searching for patterns that are related to Gleason pattern. And then based on minority and majority of these Gleason pattern, the pathologist would decide on the group grade of the severity of the cancer based on the inspection. So the ICUP grade runs from 1 to 5, and in this image we can see how it's been done. So first of all, on the left we can see that how a benign or normal, let's say benign cell look like normal cell with a tissue with small cell, well structured, and then as we can see with the increase of the severity with ISUP grade 2, 3, 4, we can see that it becomes more unstructured and bigger glands inside the cells. And if we look at the whole biopsy here, we can see that there are two patterns. One pattern marked up with the blue, and other pattern is marked up by the red. And we can see that the majority of the Gleason patterns are 3, and the minority are 4. And then if we do the composition, we can see that 3 plus 4, in terms of 3 as majority, that means that it's ISUP grade 2, which is less severe. So it goes from 1 to 5, where 5 is the most severe. And then here we use some techniques for the pre-processing of these images. So as we can see on the left, the biopsy has a lot of the majority of the slide would have white space. So what we did is we performed tiling on this slide, and then so we can remove the background, the white area, and then choose the most dense tissue that can help us in the diagnosis. And then based on that, the ones that we pick, we do different types of augmentations. We do rotation as example, or we can have 2 different tissues just to have a relevant noise on each one of those tissues. And then we concatenate them. We do, the standard flow of normalization. And then we resize it in a way that could fit into the fixed model. And here, as example, we have the ISUP grade. So each one, we use one hot encoding to represent each one of those grades as a class. So of course, this problem could be solved either by binary classification of each one, and then based on that, based on the score of the sigmoid for the positive class, we choose the most dominant one, or we can do multi-class classification where we can see the probability of each one of those grades. So the dataset is relatively large dataset. It's one of the largest datasets that are available in pathology. It's consists of almost 10 to 11,000 cases, where some of them is from the Radboud University Medical Center in Netherlands, and it has like 5,000 biopsies. So from each patient, we take multiple biopsies, train students that did the annotation, and then for the Karolinska in Sweden, we had another around 4,000, where there is single experienced pathologists. And this is for the reason of having more diverse opinions of pathology protocols, also different tiers. In this case, like there is some overlap, but there's the Netherlands has a larger, wider interval of years. And then here we can see the distribution of the grades. We can see there is class imbalance. So that's why we use different techniques that can balance those classes. Again, as we can see here, this is the tissue after tiling and normalization. Sorry for the noise. And then we want to build an AI model. So first we do the image processing, as we mentioned before. We do the tiling. We choose different sizes of those tiles, and then we train also different models based on these sizes, because we want to understand the performance that would be unrelated to the size of the tiling that we are choosing. And then we do, as I mentioned, image augmentation. We used a couple of different techniques. In that case, one of them is the efficient net, which is known as important for, I mean, focused on high resolution images, given the architecture where we scale between the width of the convolutional nets and the depth of the number of layers. And it's efficient in terms of the features. So it's more efficient to train such a model. It helps also in generalizability given these reduced number of features. And then we train and test. We perform five-fold cross-validation. We hold out one set, and we train on other four sets. Then we report the results on each one of those test sets, and we average the results. So we use different types of loss functions. In this case, because we did binary classification for each one of those classes, we used a binary cross entropy. And then we used the different learning rates based on the training needs, performance of the training. So here we can see the different versions of the efficient net, and we can see the baseline. So we trained the state of the art that was published in the literature, and we trained it on this large scale data set because many research work would use their own data set and evaluate on their own data set. But then when it's externally validated, also here as Dr. Jürgen mentioned, that we need models that can perform also in real world, and when are evaluated on external set that would be reliable for being able to be used in real world and beyond the report of the research. So so as we can see here, although the B7 has it has increasing amount of features that hyperparameters that are optimized, but we can see the B1 that best outperformed all the rest, and it outperformed on this large scale data set the baseline. And again, so we trained, in this case, we held our data from center that we didn't see, and we trained all of the models on one time. This specific case. So what we wanted to also evaluate is the efficiency of, this is like the architecture of the efficient net. And as we can see, I don't know how much time do we have, so I'll just move on to the next usability evaluation of the model. But as we can see here, the efficientness has reduced computational costs, lower memory requirements, transferable features, improved training efficiency in terms of training process, and also the generalizability. It's generalizability. So also again, so we showed the results there, and then the motivation behind the web app prototype. So we can think about what model is performing better than the other model, but still in real world we want to evaluate the usability and how good are these models performing, how usable, how easy to communicate the outcomes of these models with the clinical team. And it could be to, of course, to any other domain where we develop AI models and we want to communicate the outcomes with the user or with any consumer of these AI models. So we developed this, as I mentioned, we developed this model, and then we gathered feedback from pathologists and medical practitioners, and then we evaluated that. So So this is the web tool that we developed. It's a web tool that in terms of technology, we used Flask because our models are developed in Python, and the Flask framework is the, as in our perspective, is like the most, let's say, uh, friendly and efficient framework that we can deploy these types of models. And we were able to build visual user interface where the pathologist can upload the image of a scanned biopsy, whole slide image, and can upload it to the system. So as we can see here on the back end, we have our AI algorithm, and then we can see here that once the pathologist would click that submit, we would have different views. One view would be the donut charts that are showing, communicating the probability of each one of those ISUP grades in terms of the cancer severity, on the prostate cancer severity. And as we can see here on the right side of like donut chart, we can see that the most dominant is ISUP grade 4. And also we utilize in terms of multifaceted, we use the size of the portion of the donut chart as the confidence and the probability actually of the grading of the ISUP grade 4. And we use the red because it's severe. On the left one, we showed only the two most dominant ISUP grades, and we utilized hover over where the pathologist can put the cursor, can navigate the cursor to the area and see what is the probability of this ISUP grade. In this case, it's 4. So additional type of let's say of AI visualization is, do we want to show all the information immediately in one screen or theme? So we measure two options. One option is that we have these buttons where the pathologist can click and see the biopsy. We visualize it. I can see the demographics. I can see a detailed summary where we utilize natural language processing to summarize the reports of the patients. And then when clicking on each one of those would provide more information. The other option is to simply show all this information together with the scoring and with the donut charts in one screen. And then we collected feedback from the pathology. As we can see here, there are different types of information that we present. And for the usability and for the effort and mental demand that is demand of this tool, we use the NASA task load index that can measure these metrics. And we had 6 sections or screens that we wanted to evaluate. We measured the ease of use, the understanding, and the acceptability of these AI tools. And then we had the section, those are the sections actually, and how many ratings per section. On the right hand, we can see what are the metrics that are used. So we see the mental demand on a scale of 20. The mental demand, the lowest is the less mental needed, the less mental effort needed. Then physical demand, temporal demand, performance, effort, and frustration. Measuring frustration of the user. Okay, so this is the results of the study. And we can see that in terms of acceptability, we had 7 out of 7, which is relatively high acceptability in terms of pathologists, where we say that the pathologists are accepting working with the AI tools and would like to work with AI AI as part of the clinical team, AI in the loop. And then the ease of use would be 6.5 over 7, and the ease of understanding is 5.5 over 7. Although this score is good, but we can see that, you know, although we are trying to make these AI outcomes more you know, understandable and explainable, still there is a challenge in understanding those results. So, you know, think about, we're just giving the probability to the clinical team, and think of like the ease of understanding, or, you know, or the trust that they have. So in this case, we show some additional information about the patient, some summary about the patient. We show the biopsy, and we have 2 different, we call it evidence based kind of diagnosis, where we show also segmentation in the pixel level and in patch level. So we do the pixel level in terms of grading of the Gleason score, because the ISUP grade is in the biopsy level, whole slide image level. When we take pixels, we use the Gleason score, which is based on the Gleason pattern. And then this way we use we provide pixel level and also patch level segmentation of those Gleason areas, where the pathologist can see, and we color it also based on the severity, where the pathologist can see, okay, the ISUP grade is 4. Then they can go into the biopsy and see the areas that we marked up, and you know, focus on those areas to make sure that this grading is accurate and can, you know, trust, and this would help in a more efficient flow of the diagnosis. So I would read some of the comments, like some of the comments were of the patients as example. Some of pathologist, one user would say, it's good, a little more detail on the Gleason score graphic would be useful, and then it would, you know, address more healthcare audience. So in this case, we provided information about the patient, but the pathologist would say they want more information that has a family history of the prostate cancer presence. So the reason behind this study is that we want to improve our developed tool to be more useful, to be more acceptable, to be more understandable by the pathologist, and also to be enriched by the comments, as example, by the review, feedback that they provided, as example, the history of prostate. So we worked with pathologists on developing these models. We have collaborators as pathologists, but again, when the pathologists would take a survey like the ones that we provided, they would provide a more thorough feedback and more informative feedback. So as example, they would like to open a special viewer for the pathology, so they can already inspect those areas. Yeah, and then some would say, yeah, I want the whole information in the same screen, like the donut chart, the other information about the patient. It would be useful rather than clicking on the button. And this was part of the, you know, what we wanted to evaluate. And then so for future, so those are two papers that we published based on the study and the developed algorithms with our collaborators. Yeah. And then, so if there are any questions, but I would like to say that in terms of future work that we have is we would like to, again, externally validate those algorithms on new data sets from different populations on different scanners, as example, because we use the scanners that it's called GT450, Apereo GT450 or Hamamatsu. So there are so many scanners that the diagnosis can change based on as example, the resolution of these scanners. So we would like to evaluate on that. We would like to have more our data set to include more diverse pathology opinions, and then we can from different areas of the US or the globe, so we can see because in different pathology organizations there are different protocols that they use, and then it changed the diagnosis. So we would like our training set to be more diverse, so we can be more generalizable and have more variability in our data in this case, and reflect the challenges of the variability between pathologists. One of the algorithms, as example, that we used is in the segmentation of these pixel area of these pixel classification or the segmentation of the areas, but in classification of pixel for the Gleason pattern. What we use is we use staple algorithm that is based on voting. We had in some data we had 6 pathologists, and then we did voting based on the staple algorithm to be able to give the score. So we had also in some cases to try and understand if we have ties. So what do we do? So we tried different techniques. As example, the majority of this area where the pixel exists. So these are like different challenges that we face as part of this research, and we are trying to make it more usable, productionable research. We are trying to translate this research. We developed algorithm, but we want to translate it into the clinics so that pathologists can use it, so that the healthcare team can use it. And thank you so much. Thank you for having me.
Thank you, Dr. Saeed. Thank you so much for the beautiful lecture.
Thank you. Thank you. I appreciate that.
Thank
So
you,
if there are any questions, I can take questions, or again, you can either send to Professor Dana, the chair, or Kiran, or you can send me to email. Yeah, and thank you for listening.
Hi, actually, that's one of the research I worked on, but I worked on the genomics side. So I think I'd like to stay in contact, could actually work in collaborations, because I work on the genome. So I actually worked on LNCAP cells. So what I think you could do in terms of expansion, now validation the model, yes, I can definitely help you with that. But looking at genomes like IGF-1 and BRCA1 and 2, which are common genes that are mutated in the LNCAP cells that are usually differentially expressed, it can actually help predict and faster, because that's what I'm working on, trying to see if we can actually detect prostate cancer earlier on as well, as opposed to just using the biopsies. But obviously, biopsies mean you're presenting, you're actually presenting. But if you can do it from maybe perhaps looking at when you get blood works and we get some of these tests done, and you look at the genomes, we could probably start using that to try and do early detection, much earlier detection for prostate cancer.
Professor Saeed, you are on mute.
Unmute.
Yeah. So some of what we work on is you have the TCGA dataset in the NIH website that is publicly available, where we have the biopsy and the transcriptome. So we downloaded the dataset. We're going to work on that in terms of like multi-modal data. But definitely we can, if you have some other areas that we can perform early detection, and then we find these information probably with our collaborators. If we have this information in their data set already, we can evaluate, early detection compared to detection with like biopsy, because 80% of the biopsies are benign today. So even if we perform, genetics and or genome and biopsy, and we collect them over time, this would also be count as early detection.
Early detection.
Helps in the early detection process. Yeah, definitely. We can discuss that later. Sure. Okay, thank you everyone then.
Thank you, Professor Amal. Thank you for a great presentation.